So in this video and the sequence of videos that follow, I go over the matrix inverse and its properties. So I have a number of goals. In the videos, this one and the future ones, we'll be talking about Markov chains as a reason to use matrix multiplication and also to hint at an interesting computation problem we will have in the future. We'll then talk about the multiplicative inverse, how it comes about, why we need it, how to define it. In later videos, we'll talk about elementary matrices in order to try to tease out the connection between matrix multiplication and various row operations. That will then lead into eventually how to use Gaussian elimination in order to find the inverse of a matrix. And at the very end, the last video, we introduced the fundamental theorem of invertible matrices, at least the first version. Obviously, this is a hugely important theorem because otherwise it would not be called a fundamental theorem of the course. So let's get started. Markov chains. A market research team is going to conduct a survey on population's preference in toothpaste. There's going to be only two brands that the population uses, brand A and brand B. So in 1 month, 70% of people who use brand A will stick with it. 30% will swap the brand B. And in 1 month, 80% of people who choose brand B will stick with it, and 20% of them will swap the brand A. Now, what I want to know then is there a way for us to predict in the future what percentage of people will prefer brand A over brand B? To do so, let's suppose that we start off with that in the beginning, the preference is split 50-50. So 50% of people prefer brand A, 50% of people prefer brand B. So after 4 months, I want to know the preference of people. What percentage of people will now prefer brand A and what percentage of people will now prefer brand B. So let's suppose that A is going to represent the percent of people that prefer brand A. We'll represent that percentage as a decimal. Capital B will then represent the percent of people that prefer brand B, again, as a percentage, as a decimal. I want to know then what percentage of people will prefer brand A after 1 month. Well, of those who prefer brand A right now, that's what A equals. 70% of them will stick with it. Of those people who prefer brand B, that's B, that number, 20% of them will swap the brand A. So if I just take those numbers, multiply them, and add them together, I'll then have the new percentage of people in 1 month who will prefer brand A. You can do the exact same thing for brand B. The interesting thing is look at the left-hand side of these equations. Notice that they're linear equations. I can actually represent this entire operation as a matrix multiplication. The matrix multiplication would just be this matrix times a vector, which will be the old percentages for A and B. That matrix multiplication will give me a new vector, and the new vector is the new percentage of A and B, as in terms of people who would prefer brand A and percentage of people that prefer brand B. As an example, I'll show you some numbers. So let's suppose then you start off 50%. 50% of people prefer brand A, 50% of people prefer brand B. Then this particular matrix multiplication will then represent a vector, so that that vector will give me the amount of people that prefer brand A and the percentage of people that prefer brand B, again, after 1 month. So that's a vector now. That product, don't think of it as a product. Think of it as a vector. It's a 2x1 in the end. So since that's a vector, I can then take that vector and again multiply it by this matrix. And by doing so, that's how much that will also then be a 2x1 vector. And that vector will then give you the percentage of people that prefer brand A and the percentage of people that prefer brand B. Notice that you can reassociate that product so that you can write the left-hand side as a power of that matrix. Aha! So if a power of that matrix and then multiply by the original percentage vectors will give you the percent of people that prefer brand A and brand B after 2 months, I can then use a hand-wavy induction to say that it seems reasonable that if I want to know what percentage of people will prefer brand A and brand B after 4 months, I just take that matrix to the 4th power and multiply it by my original initial vector. That would be it. And that's right. Now, in order to argue that, I would need to do I would apply a formal use of induction, which in this class, I'm actually trying to avoid like crazy because you have never been taught induction. And I don't like having students using proof techniques they've never seen before in their lives. So I try to avoid. Instead, we do hand wavy induction, which means we believe it's true because the pattern just keeps going. So what's interesting about this process then is that I can now, if you want, we could figure out what percentage of people will prefer brand A and brand B after N months. So what happens then if we just let time go on forever? Just let it keep passing. Is there a place, a percentage that these things settle down to eventually? And there is. It's just that we have no way to figure it out right now. We have no way numerically to figure it out. Well, no, algebraically. Numerically, we can guess at it. We would just take this to a huge power, multiply it by the vector 0.5, 0.5, and see what happens, right? But that would be guessing, though, yeah, and we don't want to do that. So this is something we need to pursue in the future. What happens if we take a matrix to a large power? Right now, we have no way to figure out what that would become. Okay, so going back to the original topic, we would want to talk about solving linear equations. So we're going to do a shift. The simplest linear equation that you have in algebra is ax equals b, where a is a non-zero number. You think of it as just divide by a, the solution is x equals b over a. That's true, but you're now skipping through all the algebra to do it. You're skipping through a lot of things to do so. So realize that if you go and divide by a, there's no such thing. There's no such thing as dividing by a. The only thing you have in arithmetic is addition and multiplication. That's it. So everything else is notation. So when you say divide by a, you really mean multiply by the multiplicative inverse. That's what this is right here. You are multiplying by the multiplicative inverse. So, and you're doing that on both sides of the equation on the left. Once you do that multiplication, you can then reassociate the product to pair up the a with its multiplicative inverse as a product, because then that becomes 1. And we know 1 times x then becomes x. That's the sequence of algebra. So I like to do the same thing with matrices. To do so, though, we need a small shift. So let's suppose that we're looking at a linear system of linear equations. Let's suppose there's n of them, and let's suppose there's n variables. You can then take that linear system and write it as an algebra equation expressed as matrix products as ax equals b. It's just that a is the coefficient matrix of the system. X is a column vector of all the unknown variables, and b is a column vector that corresponds to all the constants that the equations are equal to. So then now you have made that kind of shift. Instead of worrying about lots and lots and lots of linear equations, we have only one, just one. So you might wonder, can we just divide by a? Just divide by the matrix A on both sides, and then that should be the answer. If only. Let's see what happens. Let's start off with the equation ax equals b. And then let's just divide by a. The minute you do that, you should notice, though, that doesn't make any sense. We don't have an operation of a scalar divided by a matrix yet. We don't, and we never really will. So then that's meaningless. You can't take 1 and divide by a. So if that doesn't exist, then we can't use this technique. Well, we can, but we have to think about it the right way, like we did when I went and showed you how to solve the equation ax equals b when we were just doing with numbers. You don't divide by a. You multiply by its multiplicative inverse. So trying to get analogs to what you saw before, what we really want is a matrix. We want a matrix so that that matrix times a would give you the identity element, because the identity element, in this case, the identity element in matrices, that's the identity matrix, because that's our equivalent to 1 in matrices. Don't worry about right now how to find it. Let's just see if we had it, how could we use it? So notice that if you start off with the original equation, ax equals b, you can multiply on the left by the multiplicative inverse. You could then reassociate, just like we did before. That reassociation would then become the identity matrix, but we know the identity matrix times x is just x, and that gives you the solution. So if we only had this inverse matrix, it'd be really easy to solve the system. We have a couple very serious problems that the rest of the videos tackle. And that is, does it exist? The second question would be, is, well, what the hell is it? There's other questions also. What kind of algebraic properties does it possess? And another one would be, is there only one answer? I guess another question would be, is how does this connect with all the things we've been taught so far? These are all questions we're going to discuss in the sequence of videos you're about to see. None of them are very difficult, but it is, though, kind of time consuming. So inverses. So the definition of inverses are going to be this. We will say that a square matrix, is going to have an inverse called A prime that has to be the same size if you take A times A prime or A prime times A, you get the corresponding same size identity matrix. If that happens, then you say that A is invertible and that A prime is the inverse. Now, notice that the definition has a little bit more than what I just implied, because before I only required that A prime times A equals the identity. Now I require that both multiplications equals the identity. One of the videos that we do in this particular sequence will show you that actually we don't need both. The minute you know that a product of matrices of the same size equals the identity, then the matrices are inverses of each other. It happens instantly. You don't have to check the other way. But we're going to need all the theorems for these videos in order to explain why, to get that simple result. So it's really easy to apply. If you think that you have a matrix and you claim that this is the inverse, all you got to do is multiply them and multiply them in the other order and show you the identity both ways. So for example, if A is this matrix and A prime is that matrix, then A has an inverse. It's A prime. And A is invertible, because if you take the product of those two matrices in both orders, you get the identity matrix. It's really, really easy to check. It's just a matter of just cranking out the numerical concept. Now, there are some things here, though, that are fairly important. You know that with numbers, certain numbers do not have multiplicative inverses. You think of it as can't divide by that thing. That doesn't make sense. There's no division. You can just use that word, a sequence of phrases for you to make it easier for you to digest things. So then only certain things have multiplicative inverses with real numbers. The only thing that does not have a multiplicative inverse in numbers is 0. You can't divide by 0. So you would expect the same thing with matrices. If you have the 0 matrix, you expect that it doesn't have an inverse. And it's really easy to check it. The 0 matrix, no matter what the size is, any square 0 matrix will never have an inverse. And the reason is just suppose it had one for a second. See what it means. If it did have an inverse, that would mean then that the 0 matrix times its inverse has got to be the identity matrix. So that means that the product would have entries that are not 0. But it's the 0 matrix. So if you take the 0 matrix times this supposed matrix, it's going to be the 0 matrix. So it can't be the 0 matrix and the identity at the same time. So that's just impossible. My assumption that it's invertible is false. So the 0 matrix has no inverse. But though, with real numbers, the only thing that does not have a multiplicative inverse is 0. Well, but that's not true with matrices. There are non-zero matrices that still don't have inverses. It's sadly more complicated. Curse you, matrix multiplication. So let's see why. Here's one example. This matrix, that non-zero matrix, doesn't have an inverse. We'll do the same argument. We'll assume it does, and I'll show you where things go wrong. So let's suppose it has an inverse. We'll just call it A prime. Notice that A times A prime, or A prime times A, is the identity matrix. That's just by definition. But also, if you look in particular, look at A prime times A, and look at the second column. Well, by column matrix multiplication, the second column of A prime times A would be A prime times the second column of A. But the second column of A is nothing but a vector of zeros, which means that the product would be a vector of zeros. It'd be a 0 vector. So the second column of this product would have only zeros in it. Well, but I just said that the product should be the identity matrix. So every column has a 1 in it somewhere. That's impossible. That's impossible. So this non-zero matrix, unfortunately, does not have an inverse. So we at least should tackle or end this particular video with at least one theorem that makes us feel a little better. And that is, if there is a matrix, if there is an inverse, there's only one. So from now on, we'll just be able to give it a special name. Why that's true is, again, interesting to see. It's not something that's obvious. We certainly have to explain why. So the common way to show that there's only one thing of something is to suppose for a second there's actually two of them, and then to prove they're equal. That would then mean that there can't be two. There's only ever one. So let's just do that. Let's pretend that A prime and A double prime are both inverses. So if they're both inverses, then by definition, both sides, we would have that A prime times A is the identity matrix, and A times A double prime is also the same identity matrix. That's going to imply they're equal because of this clever use of algebra. Notice that A prime is equal to A prime times the identity matrix. That's just matrix multiplication. But the identity matrix can be written as A times A double prime. So then I just substitute that in. That particular matrix product has a certain associate order of the parentheses. I can reassociate those parentheses to take it first A prime times A, but A prime times A is the identity matrix. I would then have the identity matrix times A double prime, and that's A double prime. So if you look at the beginning and you look at the end, you realize they're equal. So that means then that a matrix, if it has an inverse, there's only ever one. It's unique. That's great. So the minute we have here is A inverse, it's the inverse. There's only one. Doesn't matter how we get there. That's the inverse. So because of that, we'll define it specially from now on. So if A is an invertible matrix, from now on, we're going to call the inverse A to the power of -1, because that's essentially what we do with real numbers. You just don't remember it. It's been a long time. But the multiplicative inverse of 2, you think of it as 1 over 2. It's actually 2 to the -1 power. It's just you've forgotten why you write it that way. 1 over 2 is a notational device to make it easier for you to visualize things. The actual definition is 2 to the -1. Okay, cool. I think that's enough for that video. And we'll go on next video to talking about solving systems.